Hi, my name is Stephane de la Rue du Can, and it is my pleasure today to take part of the discussion panel of the Energy Management Center of Kerala. I am a researcher at Lawrence Berkeley National Laboratory, or Berkeley Lab as we more commonly call it. Berkeley Lab is a research laboratory of the U.S. Department of Energy and is managed and operated by the University of California. We are more than 4,000 employees, but most of the people work on energy basic research. Our department focuses on applied research. We develop analytical and experimental methods and tools to assess the technical, economic, and market potential of emerging technologies. And we look also at the associated impact of those emerging technologies. I have been working at Lawrence Berkeley National Lab for the last 17 years, and my work mostly focuses on energy efficiency. I am in the International Energy Analysis Department, so I have been working on partnership with different countries around the world. I had the pleasure to work with several organizations in India, among which EMC and TERI, so I am very pleased today to be part of this webinar. I will also note that I am a lead author of the industry chapter of the next IPCC assessment report that will be published next year. A large focus of the chapter will cover industry decarbonization strategies. The industry sector is poised with the significant challenge of having to continue to grow, to provide essential materials and products for economic development, and at the same time reduce its environmental impacts. The environmental impacts of the industry sector has consequences on climate change, air pollution, water use, soil contamination, all which have impact on health. Globally, the industry sector represents the largest source of GHG emissions. According to the IPCC report that was published in 2014, 32% of global GHG are direct consequences of activities in the industrial sector, as can be seen on the graph on the right side. The industry sector represents therefore an important sector to focus on when it comes to decarbonization. However, this sector is often characterized as hard to decarbonize due to its heterogeneity and the difficulty to find one solution for all. The sector is also very strategic for economic growth and employment, so it has often been sheltered from environmental and climate policies. The sector is composed of highly diverse subsectors, each employing energy for diverse end use in many different industrial processes. What is interesting to note is that only three sectors, iron and steel, cement and chemicals, represent 2/3 of global industry GHG emissions. In terms of countries, China is by far the largest source of global emissions related to industry activities, with slightly more than 50% of global emission. India, on the other hand, represents only 7%. This is the result of rapid economic development in China, with GDP growing ninefold since 1990, fueled by demand for urbanization, infrastructure development, and the penetration of new equipment. In 20 years, China has become the largest producer of cement, steel, aluminium, and ammonia, and is among the largest countries producing chemicals, petroleum products, and other basic materials that require a significant amount of energy in their production. India, who is also home of 1 billion inhabitants, has experienced a slower economic growth in the same period. But the emergence of a growing middle class with aspiration for a better quality of life is contributing to growing urbanization favored by policy reform on planned public infrastructure investment. The International Energy Agency ETP model of 2017, in the baseline scenario, projects that industry emissions, just counting emissions from fuel and cement process, will more than double by 2050 if no new commitments are made. They also forecast that from those projected emission, China will represent 30% and India will represent 20%. So there is no one pathway for the decarbonization of the industry sector, but multiple pathways possible. This graph represents 5 of the major decarbonization pathways strategy that can be considered. The first one is material management, which is a combination of material efficiency and circular economy, which counts on longer life products, lighter buildings, etc., that can play a major role in reducing our emission industrial footprint by requiring less material. The second one is energy efficiency, which can reduce the need for burning fuel. The third one is electrification, which I will talk a little bit more longer. Then fuel switching to zero carbon fuel, like for example renewable natural gas or biomass. And then the last one is CCUS, or carbon capture, utilization and storage. So coming back to electrification, we can identify 4 main categories in that pathway. The first one is electrifying heat process by using existing technology that are, for example, electric arc furnace, induction, etc. Second is in the application of direct renewable energy in heating process, and I will come back to that in another slide. The third one is to use on-site or grid power generation use from solar PV and wind turbines. And the fourth one is to consider emerging technologies such as electrolysis for iron making and hydrogen, for example. One of the reasons why decarbonization of the industry sector is considered as hard to decarbonize is because most energy-intensive sectors require high heat, process heat, such as iron and steel, cement, glass, etc., that cannot be electrified easily. According to different research groups, electrification is technically possible for all industrial processes. However, the electrification pathways is also difficult in industry because of the low cost of coal and other fossil fuel, and the typically much higher relative cost for electrified heating. The utilization of electric heat for industrial processes is generally targeted to specific end use. Sectors such as specialized material production, heating, drying, surface curing, and melting are using electric technologies. For high heat, it is possible to use indirect electrification by producing hydrogen from water electrolysis using renewable energy, and then use hydrogen as an energy carrier or as an energy feedstock. And in some potentially, it will be also possible to use hydrogen as a reducing agent to produce iron. We have experienced recently spectacular drop in renewable energy cost, with solar PV power purchase agreements falling to less than $30 per megawatt hours. This, coupled with energy storage cost also dropping significantly, offers new opportunity to favoring electricity usage as a strategy to decarbonize industry sector. This has led to the emergence of startup companies that are combining the development of software solutions with the installation of electric heat equipment at industrial facilities to benefit of low renewable energy prices. Of course, this type of solution, however, relies on dynamic pricing, which is yet to be rolled out more significantly. This diagram comes from the Environmental Protection Agency in the US, and it illustrates very well how renewable energy can be applied directly in the industry sector. It shows 9 different renewable heating and cooling technologies on the left side of the graph. And it shows common end user application of those technology in the industry sector shaded in the background of the graph. On the vertical axis, you can see the different temperature bins in which those technology can be applied. So, for example, you can see that heat pump, on-glaze, and transparent, and also somewhat flat plate renewable technology can be only applied to low temperature level, for example, most specifically for media heating. While on the other side, evacuated tube can raise the temperature higher and can be applied to more end-use technologies like cooking, pressurizing, sterilizing, bleaching, or industrial distillation, concentration, drying, and kilning, and chemical and other higher temperature processes. The renewable energy that promise more higher temperature levels are concentrating solar and also obviously wood biomass. Information on those different technology and how they can be applied in the industry sector is available on the EPA website, where you can see on the right hand side the website, the link to the website. So finally, this is my last slide, and it's about the implication in terms of policy. Determination of pathways for maximum electrification of industry will need support from policy and programs. As explained earlier, the industry sector has a set of preconditions, such as being a strategic sector for growth, being very heterogeneous, and lacking of single technology solution, and has been sheltered often from stringent environmental and climate policies. In California, for example, while we have clear reduction roadmap policies and activities for the energy, building, and transport sectors to achieve 80% reduction by 2045, industry remains to be addressed and has been sheltered from the cap and trade program. Moreover, the low cost of fossil fuel compared to electrified heating require specific attention so that industry sector can also benefit from very low renewable energy prices through new pricing signals. Innovating and novel policies are therefore critically needed in the industry sector. The chart on the left is a scale representing technology readiness level, TRL, which is an indication used in research and development and innovation of technologies to indicate the maturity stage in which the technology is. It can be seen as an indicator of how far technology is being commercially available. Roughly, this can be disaggregated in a basic research, lab technology development, or commercially available technologies. For each of these stages, different policies are needed to nurture and grow the emerging decarbonization technology. In summary, technology with very low TRL levels need policy intervention that relates to technology push, such as lab research, consortium for innovation, demonstration projects, and also impact economic and environmental impact assessment reports or studies. When the technology is more advanced and have a higher TRL, then different type of policy are needed, more what we would call more market pull type of policy, in which case you need standardization, specification of the technology to be more readily applicable in the market. You have labels to see the pros and cons of the technologies, and you can have also procurement, public procurement that can help pull the technology in the market, and then also financial incentives to scale up the technology in the market. So thank you very much for listening. Here are my contact information, and I look forward for the discussion. Thank you.